Good afternoon, everyone, and welcome to the second session of design engineering. And today we will deal with the general design procedure, which we have discussed yesterday itself. So today, a brief of that, and then we'll directly switch over to the introduction of joints, bolted, riveted, and welded. So yesterday we have very much focused on the general design procedure for machine elements. So first of all, when we say design procedure, the procedure should not be a rigid one, but it will help us in determining the general line of action for the design of new component or new mechanical element. Now, first of all, we must recall the basic design procedure when we expect some demand, some requirement from the customer. We expect demand from the customer itself, and then we'll have the rough draft, then we'll have the synthesis of mechanism, then final drawing, then market survey, and then we will launch the product. So in between these procedural lines, there is no rigidity at all. That's why it is generally said that design by empirical relation and design by judgment. There is a standard way where we have to follow the procedure, and the other one is design by judgment. Yesterday I have discussed one example wherein a tabletop is to be fixed using some screws. So you need not have to calculate the forces because it can be very well judged by the expertise of the individual itself. So today we will discuss the design of joints. Now, how to define joints? Mechanical joints, since we are dealing with the mechanical engineering design, so mechanical joints are the system of connected members. Now, when I say system of connected members or connected bodies, it means that body will transfer some force. That body will be put to some stress, some tension, some compression, shear, torsion, etc., etc. So accordingly, we have to design these joints. For example, nut and bolt. This is one of the joint. Welded. This is one of the joint. Then your rivets, one of the joint. So out of these, since these joints are very much known to us, in engineering design, it is classified as permanent joint, semi-permanent joint, and temporary joint. When I say permanent joint, it means that both the connecting parts are permanently joined. Both the joint and the joining components are required to be completely destroyed for disassembly. Now, when I say I have joined these two plates, okay, and if I want these plates to be disassembled, then in this case, what we have to do, we have to completely destroy the joint. When I say I'm completely destroying the joint, it means that both the joining element and the parent metal surface gets destroyed. So such type of joint will be known as a permanent joint. And the examples are welded joints, braced joints, etc. The next type, which is again very important, is a semi-permanent joint. Now, when we say semi-permanent, it means that both the connecting parts are fixed by a permanent joining element, which is required to be destroyed. For dismantling the joint. Parent metal will not be disturbed. Just take the example of a riveted joint. So after some time, we'll go through the riveted joints also, the diagram itself. but the joint at the hub and blade of the fan, that is riveted joint. The joint on the frying pan and the handle, between the frying pan and the handle, that is riveted joint. The joint on the body of bus, that is riveted joint. Now, if you want to dismantle this joint, in that case, that rivet is to be destroyed completely. But the parent plates or the parent element will not get any jerk, a significant jerk, or the what we can say the destruction will not be there. The quantum of destruction will not be there. So in this case, we say this is semi-permanent joint. Riveted joints are semi-permanent. The next one is a temporary joint. Temporary joint means both the joining elements can be easily connected or disconnected. That's why I'm putting this before you, that these temporary joints are the most widely used joints, such as nut and bolts or bolt or screw joints, knuckle joint, quarter joint, turnbuckle, etc. Sometimes coupler nut is also used in place of turnbuckle. Now just see this bottle. The joint. This is basically the joint. This is the joint. So if I want to dismantle or disassemble it, it is very easy for me. Neither the joining or the parent metal, nobody is getting hurt or destroyed. Known as a temporary joint. And I think it is quite okay with you to get an understanding of how we classify joints. So first of all, we will go through the details of temporary joints, of which bolted joints we will discuss. So this one is the generalized geometry used for the design of bolt or screw joints. Generally a temporary joint, obviously there will be two plates, two elements for joining. So here two components will be there, generally known as nut and bolt. Nut and bolts holds the plate, elements, components, parts in the machines and gives a tightening effect for a large area of application. Highly reliable in operation. No such skilled labor is required for assembly and disassembly. Now, as far as design is concerned, important terms used in the design of screw threads. See, a screw thread is generally made out of a solid bar, out of this solid bar. Okay, so this is the solid bar. Just take for the consideration the solid bar. Now, this solid bar is generally known as a shank. It is having some diameter D of say 50 mm. So it will be a shank. It will be known as a shank. Next, we will put this on a lathe machine and we will thread it. With some V tool having included angle as 60 degree. Then in that case, the metal will be removed in this fashion. So this plain portion will be known as shank portion, and this portion, say in our video, it is red portion known as threaded portion. Now look at the minor details at this PowerPoint. Pitch, distance between two consecutive crest or trough, or simply two threads. Angle of thread is defined the included angle. The upper portion of the thread is known as flank. This is crest, root. Then different diameters we generally or nominally use. That is nominal diameter, the outside diameter. The outside diameter is known as major diameter or nominal diameter. The smallest diameter is known as minor diameter, and there is an average diameter known as pitch, circle or pitch diameter. So these are the three diameters which will influence the calculation and the strength criteria of design of bolts. So whenever we want to design a bolt, we must understand that where the stress, where the stress, or at which portion the stress will be more. Now look at this diagram. We can say that, sir, this part is solid, known as shank. This is threaded. Some material is removed out of that. So obviously the strength of these two portions will not be same. And naturally the portion which is on my right hand side or right hand side of the screen is obviously having less material as compared to this, and hence it is more vulnerable to the stresses or to the failure. So we must say that we have to defend it, we have to save this component, this threaded portion. So the next is designation. Now generally bolts are designated by the nominal diameter. Generally the nominal diameter, such as M12, M14, where M stands for nominal diameter. Sometimes tolerance grades are also added. M68D, this includes the tolerance grade. Now we must discuss how this bolted joint or screwed joint will fail. This is the next target before us. That is how to determine the modes of failure, possible modes of failure of bolt. Now look at this diagram wherein we can say that the bolt will fail. The bolt will fail. How the bolt will fail? It will fail in. Now when I say in, it means that it depends on application of bolt also. It depends on application of bolts also. How it will fail. The next one. Next one, that is tensile failure of the bolt. Whenever we say that this bolt is used to fasten these two plates, obviously we will tighten the nut, and due to this tightness, it will try to compact these two plates, and obviously in return, these two plates will apply tensile load on the bolt. So in a very simple mode, we can say that tensile stress is equals to force per unit area, where area will be the least possible area, the least possible area, the least possible area, the least possible area, that is pi by 4 DC square. Why I am telling or repeating this? Because here we have got three types of diameter. Number one, major diameter. Number two, minor diameter. Number three, pitch diameter. Then why do we are considering only EC, that is root diameter or core diameter or minimum diameter? Because if our calculations are safe on minor diameter, then it will be safe for pitch diameter as well as for nominal diameter or major diameter also. So DC is the core diameter. Now, the bolt may fail in tension, sometimes it may fail in crushing, it may fail in shear. It depends on the nature of application of load. Secondary, again, going back to this diagram, we must try to understand that due to the removal of this small portion of material, what happened? What happened? Sir, obviously the strength will be reduced. It means its cross section has a sudden change in material or cross section, and hence there exists a phenomena known as, we all should know that the phenomena is stress concentration. Whenever there is an abrupt change in cross section shape and size, then there has to have stress concentration around the junction, around the holes, drill holes, around the threads, etc. The next one, shear failure of the thread. Again, if you look at the consideration and equation, it is quite clear that pi dc, again the DC. Okay, so shear strength or shear failure, where what is B, width of the thread section at the root. So width is either calculated or generally given. Crushing failure of the threads. How will you say crushing failure? Crushing failure. How will you say crushing failure? Now, whenever we screw, whenever we screw the bolt, in that case, it will be held within the nut portion. At that point, there there we have the crushing stress. Now, this crushing stress will act in between the nominal, that is the major diameter, and the root or minor diameter. That's why the area covered is pi by 4 dO square. This is outside here. dO square minus dC square. And obviously, everywhere it should be less than the permissible value of shear stress, crushing stress, etc. Where N is a number of turns, number of turns, number of turns. So this is how we will do it. The next one, shear failure of the bolt itself. This is shear failure of the threads itself. Now these are the bolts. Okay, nothing new. Again, the shear and the area would be of the bolt, that is pi by 4 d square. Here we will consider dC square. Now, using the above equations, we can calculate the strength of bolt both in tension and in shear and in crushing. These are the basic equations for the design. Next one, you might have heard pre-stress bolt and where it is required. Just take the example of two-wheelers, specifically, Activa or Access like mopeds. If you go for the repair of your tire puncture, in that case, that pre-tightening, pre-stressing of the bolt is very necessary. Hold that. Sometimes in boilers, where the upper cover is held with the help of bolts, their pre-stressing is required. So in boilers, prior to the pressure exerted by the steam or by some gases on the bolts, so that the upper cover is held at its position, first you will tighten the bolt itself. And that condition is known as pre-stressing of the bolt. So for fluid tight joints, initial stress or load will be 2840 Newton. Obviously into the diameter, that is nominal diameter, DO or D. So this initial tension or initial load will always be considered, because this will be there prior to some load by the gases, by the fluid, by any other substance on the bolts. But initially it will have to sustain all this much of load. The next one, eccentrically loaded bolted joints. These joints are the most practical joints we use in trusses, we use in large industrial sheds, we use in machine tools, everywhere. Everywhere we are using this. Machines, in machine designs and in components also. So here we will concentrate on this aspect and we will see to it. What do you mean by eccentrically loaded? If now I'll take this example of this cylinder or bottle, or let us say this component. Now if I'm applying the load, the line of action of force is exactly coinciding the center of this particular body, then it is known as axial load. This will be known as axial load. But if the line of action of force is different from the axis of the body, and I'm applying some force at this point, wherein the distance between line of action of force and axis of the body is to some extent some centimeter, millimeter, then in that case, such type of loading is known as eccentric loading. It means that it will be applied away from the CG of the system itself. Now look at this diagram wherein I can say that this plate is held by 1, 2, 3, 4 number of bolts, and the point of application is at P, which is at a distance of small e from the CG of the rivet system or the screwed system. Similar will be the case for riveted joint also. So in this case, we'll have to consider the failure of these bolts under number 1. Now, for example, please do consider the same diagram which is there, and I'm holding this for you. But just take this example. Now, at my hand, at this one, I'm having 4 bolts. Okay, so 4 bolts are there, and I'm applying some eccentric load here. So in this case, what would happen to these 4 bolts? Sir, primarily, prima facie, sir, this will turn in this fashion. It means the effect will be like this, and this is nothing but shear. Yes, this is nothing but shear. Due to this plate, the self weight of the plate itself, on application of P, it will try to move down, and these 4 bolts will try to hold it at its position, thereby creating 2 equal and opposite action known as shear. So this shearing action will prevail at these 4 points, and hence all the 4 bolts, 6 bolts, 8 bolts, whatever may be the number, will be subjected to primary shear load using this arrangement. The next one, now secondary shear. Just try to understand this fact. This is very, very, very important. Secondary shear force. Now, just look at again first. Due to this P, which is going downward direction, these 4 bolts will resist. Done. But the secondary effect of this action will be, it will try to, just look at this, it will try to rotate it, and the individual rivet or the screw at 1, 2, 3, 4 will try to oppose it. That is the meaning of resistance. All these 4 bolts, this set of 4 bolts, 6 bolts or 8 bolts will try to resist its turning moment, and that moment is generated at E, that is P into E will be the turning moment. P into E will be the turning moment for this bracket. On the same lines, I'm repeating here. Individual 1, 2, 3, 4 will try to resist that moment, turning moment. That moment is P into E, and that is resisted by the distance of each rivet and the secondary force P1 double dash, P2 double dash, P3 double dash. That is the secondary shear force at a distance of R1, R2, R3, R4 from the center of gravity of the system. That is P1 double dash R1 plus P2 double dash R2 plus P3 double dash R3 plus P4 double dash R4. It means that the secondary shear force is directly proportional to its distance from the CG of the rivet or the screw system. Thus, we will calculate a constant value. We'll calculate a constant value C. Where is what is C? P into E divided by R1 square, all the power 2 squares addition. Thus, I can say that if I want to calculate P1 double dash, that is the secondary shear force or shear load, in that case the equation would be P into E into C, P into E into say R1, C into R1, C into R2, C into R3, and likewise. So this is the basic equation. The next one, similarly P2 dash, P3 dash and P4 double dash will be calculated. Now since primary is also shear, secondary is also shear, then we'll add this. But their addition would be according to the vectorial notations. So hence, resultant shear force would be addition of primary and secondary along with the angle subtended between primary load and secondary shear load, that is theta. So in this way, we will calculate the resultant shear load on each rivet 1, 2, 3, 4, and out of R1, R2, R3, R4, whichever may be the maximum, we calculate the diameter of rivet or bolt using this relation. Now at this D, this is generalized term, this D would represent DC. This D would represent DC for bolts, and for rivet it is simply D. Next, eccentric load acting perpendicular to the plane of eccentric load. Now in this case, eccentric load acting in the plane of bolt. Say this is the plane. So eccentric load was acting in the plane of bolt. Now the case is different. Now in this case, how the things are simply, it is not in the plane. It is perpendicular to the plane. The bolts are in this plane now. Bolts will be in this fashion, and it will be perpendicular. So it will topple down this. So consider this bracket, wherein two bolts are kept in one line at a distance of L1, that is bolt number 11, and at a distance of L2, that is bolt number 2, from the tilting edge C. Okay, so the next. So here, obviously, as seen in the last slides, that all the bolts will be subjected to, because again the same thing, so it will be under shear. All the loads will be under shear. P1 dash is equals to P dash is equals to P upon all the 4 bolts, 6 bolts, 8 bolts will be under shear. Now just imagine the case, and just take the case of your hangers on the back of your door or on the walls, where we actually put our clothes. Okay, take the same example. Now when I apply some load on that particular hanger, sir, the bolt which is there in the wall, just look at this, please concentrate on this. See, this is the bolt, so bolt is there. Now if some load is applied at this arm end, then it will try to bend. Same phenomena will be used here. So now in this case, what would be the secondary shear or secondary tensile? We have to decide. Just look at this. So with this, you can say that the bolts which are at position 1 and bolts which are at position number 2. Primarily, all the 4 bolts will be subjected to shear, that is primary shear load. But secondarily, at this tilting edge, the maximum turning moment P into E, because tilting edge is nearer to bolt number 2, that is L2, the farthest end is L1, so the maximum tension will be developed along this bolt number 11, and that is represented here in this equation. Henceforth, we have to calculate equivalent tensile load, and this is the case. So the next one, eccentric load acting parallel to the plane of bolt. This is simply ceiling bracket is there, wherein primarily all the 4 or 2, 4, 6, 8 bolts will be under primary tension. Okay, and same is the condition here. Both the things would be tensile. We'll have to directly add it, and we'll get the answer. So this is how the again the same thing. Bolt at 1 would be farthest from the tilting edge, that is bolt 1 will be at farthest L1, so it will be there and the result will be calculated. Okay, so this is all about the design of screwed and bolted joint. For the sake of understanding, only for bolted joint I have taken some objective questions. You can very well go through. The bolts in the flange end of pressure vessels are usually pre-tensioned. Indicative of the following statement is true. Now, this is a case of pre-tension or pre-stressed bolts. Pre-tensioning helps you to see the pressure vessel. Pre-tensioning increases the fatigue life of bolt. Pre-tensioning reduces maximum tensile stress in the bolt. Pre-tensioning helps to reduce the effect of pressure pulses in the pressure vessel. So it is basically used to maximize, because our bolts, when subjected to direct pressure without pre-stressing, will be subjected to maximum load. So pre-tensioning reduces that maximum tensile stress in the bolts. It is already pre-stressed. So this is the case. The next one, the bolts in a rigid flange coupling connects two shafts transferring power are subjected to. And I think that this is very, very, very simple, because if flanges are there, if they fall apart, then tensile load will be there or axial load will be there. So axial force will be. The next one. Since all three topics are there today, we will go accordingly, no problem, but still we have to finish it up. Eccentrically loaded joint where the load is in the plane. So the direct shear force 20 divided by number of screws or rivets, that we divide by 4. So this, then F2 would be obviously the distance from the CG. CG will lie at half this portion, so 30 plus 15, so 15 would be there, and there it will lie the CG, and that's why 2 into 15, these two, for these two, 1, 2, 3, 4, so 1 and 4, it would be 45, and for 2 and 3, it would be the CG would be between this, so 30 divided by 2, 15. So for this distance would be 15, and this for 45, the answer would be 16 kilo. The maximum shear stress force of the assembly. Now look at this. The answer is, you please solve this. The answer is 30 kilo. And my friends, the very next and the very interesting topic, that is riveted joints, where we have seen the riveted joints. All the automobile bodies, aeroplane bodies, yes, are riveted, welded, brazed, number of, but the basic strength is given by a riveted joint if it is of permanent nature. If it is of temporary nature, then nut and bolts will be used. Now see, this is the generalized structure of any rivet. It is a shank portion having some head, hemispherical head. This head is also of some different shapes depending upon the requirement. Then this is the shank portion, solid portion, and this is the tail portion. This tail portion is kept for easy insertion in plates and sheet metal, and then it will be banged from the top so that it will flatten up so that the joint will be made. There are two types. Rivet joints are mainly of two types: lap joint and butt joint. Next one, lap joints. And my dear friends, we will cut down all this introduction part for welded, because similar is the case and similar are the joints itself. We will directly discuss the stresses point in welded, the last one. So lap joint. When one plate is kept overlapped over another and a rivet is used to join the two plates, then such type of joint is known as lap joints. Please concentrate on the diagram itself so that you can have very good idea of type. The next one, see, the previous one was lap joint, but single riveted lap joint. This is single riveted lap joint, single riveted lap joint. The next one is, see, the double riveted lap joint. Two rows are there of rivets to hold these two plates. And third, sir, zigzag. See the pattern, zigzag, zigzag. So single riveted, double riveted, zigzag lap joint, double riveted, zigzag lap joint. The next one, butt joints. Suppose we want to join these two plates. We cannot join these two plates head on because there is no arrangement to join these two plates using rivets. And henceforth, we will use a cover plate always. Let us say this is plate 1. Let us say this is plate 2. We want to join these two plates, so we'll have to compulsorily take a cover plate for this. Now this cover plate will overlap these two plates and riveting will be done. So this type of joint is known as a butt joint. So here it is using single, so single strap. The next, single riveted butt joint, single riveted butt joint, single riveted butt joint with single strap, single riveted butt joint with two strap plates, two cover plates. Strap means cover, cover plates. Single riveted, single strap, single riveted, double strap. Now next, double riveted, single strap, double riveted, double strap. So these are the joints. Okay. I hope you are getting the classification. Now, important terms, very, very, very important terms used in the design of riveted joints. See, the strength of riveted joint depends on pitch between the two rivets. Now, there are three types of pitches, the most important type. There are other also, but these types are very, very, very important. What is pitch generally? What is pitch? Simply the distance between two rivets. Here, consecutive rivets. Now see, the distance between two center of the rivet is P, known as pitch. Okay. On lateral side, next is back pitch, PB. See the distance. See the distance. Distance between two lines or two pairs of the rivet, known as back pitch. And the third type is a diagonal pitch. The distance, diagonal distance is zigzag distance. Again, the next after pitch, which is very important element, is a margin or marginal space. C. Because if you can't maintain, generally 1.5 times of diameter of rivet is kept. This margin M is generally 1.5 times of diameter of the rivet. Why? Because when we make a hole for this rivet, there are chances, if this M is narrow or low, then the plate may get a tear off. The plate may get tear off from the same diametric hole made for the rivet. So margin is again a very important aspect in the design. Now, how to calculate the strength of riveted joint? A very simple arrangement, and different types will be explained. Okay. Number one, tearing of plates. Just imagine a tensile load is applied. Okay, this applied in this fashion P, and these two plates are riveted, then it may be possible, that the plates may fail between the rivets. Yes. And what would be the distance? P, simple pitch. What is small d? The diameter. So this here it is d by 2, here it is d by 2. So this is d into thickness of the plate P. There, this would be known as tearing strength or tearing of the plates, where S1 is the allowable tensile stress of the plate. Okay. So while calculating the strength of riveted joint, the very first element is tearing of the plate. The next one, see how designer considers different types of failure so that we can save the joint. Sharing of the rivets itself may be possible. The rivet may get shear off. Yes, possible. So if the rivet is having in this fashion, if two plates are holding, or a rivet is holding two plates, then if shear occurs, then this plate will take one portion to the right and this will to the left, and the rivet will fail along one single plane. Now see the interface of these two colors. This is one single plane known as single shear of the rivet. Single shear of the rivet. Yes, it is single shear of the rivet. If there are three plates, say 1, 2, and say 3, and if the rivet, now see, in this case of single shear, the rivet gets failed in two parts. But if there are three plates, then in that case, the shear failure will occur from the two reference planes, and the number of pieces of the rivet would be 3. So if it is broken into 3 pieces, we may say that it is a double shear. If it is into 2 pieces, we may say it is single shear. Yes, sir. So this one, again, the failure of rivet will continue. Crushing of rivet. So the third type of failure is crushing. And simply the crushing is well explained by this diagram itself, wherein the adjoining surface or the element gets a bearing, or the bearing stress or the crushing stress. So this is SC into D, diameter into thickness. Obviously, this is the area surrounding the rivet. This is D into T. The next, tearing of the plate at the edge. That's why we have, I've told you, and we have discussed this. This margin is very important. This margin, the axis passing through all the rivets and the edge of the plate. So it is at least 1.5 times of diameter, so that a sufficient distance is maintained and no such casualty occurs. The efficiency, depending upon the different stresses, P1, P2, P3, it is load. We can calculate the efficiency of the joint depending upon the condition. The next one, the design of welded joints. Now see, in general, the riveted joints, there are 2 types of numericals asked. One on the circumferential or hoop stresses, and number 2, the generalized eccentric joints. So the design procedure for the riveted joint for eccentrically loaded riveted joints is exactly the same as of the bolts used in the screw joints. Okay. And as far as boiler joints are concerned, generally the boiler joints consider the circumferential or hoop stresses, wherein we have to completely design the boiler considering the riveted joints for the same. But all these failures will be considered there only. So I hope that riveted joint, based on these failures, you have understood it very well, and the equation would be in this order only. So I have discussed all the equations and finally the efficiency of your riveted joint. And the last but not the least, welded joint. Okay, I again repeat, the numericals, again, so that numericals of riveted joints will be same for eccentrically loaded, these eccentrically loaded, these eccentrically loaded screw joints. Okay, there would be all the three cases, but generally in the plane of bolt, and perpendicular to the plane of bolt or rivet would be discussed. So same equation, same procedure, only thing which is there would be, in this case here, the diameter would be root diameter or core diameter of the screw, and for us it would be the diameter of rivet, that is shank diameter D. Rest every procedure, everything is same. Okay, so I hope again and again, because two times I have repeated, sometimes people, students may ask this question, sir, you haven't given any example. I'll definitely be sharing some example, okay, in the next lecture regarding the riveted and welded. Okay, now the last one is welded. It is well known type of joint right from our childhood. All the joints, let it be rivet, let it be screw joints, because from childhood we have learned bicycle, and in bicycle all these joints are there, present there. What is welding? Welding is the process of joining two similar or dissimilar materials by fusion to provide a permanent joint. When I say permanent joint, in the very start of this lecture today, we have very well discussed, when we say permanent joint, it means that both the joining element and the parent metal will get destroyed if we disassemble it. If we disassemble it, it will be destroyed. Now, how welding is done? So, welding is done by fusion of metal, number one. Number two, by fusion of metal and with some additional inserts. Some third element is inserted and it is fused. Generally, in electric arc welding, it is electrode. So that is there. Now, the contacting surfaces are heated at high temperature. Let it be arc welding, let it be gas welding, or some argon and some. There are a number of methods of welding. We will discuss one by one, because generally the welding procedures are divided into basic categories. Where it is used in fabrication of ships, automobiles, pressure vessels, then bridges, then pipelines, nuclear fuels and explosives, ceilings, everywhere where we expect a leak-proof joint, we will use welded joints. Another quality of welding or the welded joints is, although it is of permanent nature, although it provides leak-proof joint, simultaneously it is giving you a strong joint also. Yes, again it is used to provide leak-proof joint, as well as it gives a very good strength in the components where it is being used. So from small section to very large sections of ships, welding is everywhere used. Now, just look at this types of welding, because in the question bank or question paper we have gone through, these theory questions are repeatedly being asked. So, fusion welding process, how do you classify fusion? The fusion welding process uses heat to melt the base metals. In fusion welding operation, a filler metal is generally added to the molten pool. Fusion welding process can further be subdivided into, that is, arc welding and resistance welding. Arc welding, all of us are very much acquainted with the arc welding. Resistance welding is also there. It uses electrical source and resistance to flow of current passing between the paying surfaces of two parts held together under pressure. That is the resistance welding. Solid state welding. Now this is again, I don't think it is a new type of welding, because ultrasonic welding we have studied and we have heard. Friction welding we have heard in our course, in our UG course syllabus. So solid state welding refers to joining process in which coalescence, the joint from application of pressure alone or combination of heat and pressure. You might have heard spot welding. Yes, yes. So heat and pressure. Pressure is necessary. So pressure. So diffusion welding, two surfaces are held together under the pressure at an elevated temperature and part caused by the solid state fusion. So coalescence is made by solid state fusion. So we have to fuse these two methods. Same is the case with friction and ultrasonic, where it is achieved by the heat of friction between the two surfaces. Yes. Metal to metal friction would be very high, and the welding is done at solid state. Ultrasonic welding, moderate pressure is applied between two parts, and an oscillating motion at ultrasonic frequencies used in direction parallel to the contacting surfaces. Now, these are the general types, welded types, or the joints, different types of welded joints in use. So, there it is. Lap joint or fillet joint. Lap joint or fillet joint. Now, look at these diagrams. Single transverse, it means on one side the joint will be made parallel to the edge of the plate, that is known as single transverse. Obviously it is lap joint. The plates would be overlapping plates would be there. So overlapping or single transverse. Second one, double transverse. Just look at this diagram wherein the upper end and the lower side both are welded. Third one is a parallel fillet, where the welds are done parallel to the direction of application of force. Whereas in transverse, it is perpendicular to the direction of application of force. So this is the basic type 1, that is a lap joint or fillet. The next one is butt joint. This we have studied in Revit also. Butt joint, end-to-end connection, end-to-end connection. So if you want to connect, just concentrate and try to understand this fact. So if you want to join these two plates end to end, in this case, there won't be sufficient gap. So that a filler metal can get a space in between. So the filler metal will flow over the surfaces, and the joint will not be so strong as expected or required. Hence, some material is removed intentionally in some fashion, so as to provide a gap for the filler material to get settled between the two surfaces. And hence, we can classify butt joint according to the different shape, the enforcement given, that is square butt joint, single V, single U butt joint, double V and double U butt joint. These are basically the shapes given intentionally so that the filler metal can occupy the space between the two plates. The edges are trimmed. The edges of the plates are trimmed, and the metal can sit. So these are known as butt joints. Basically, comparing the strength of lap and butt, we may say, and it is quite evident from the figure itself, that lap joint would be more stronger as compared to butt Lap joints would be more stronger as compared to butt joints. The next one. This is the basic consideration involved in the design of any weld type or joint. The shape of welded component required, the thickness of the plates to be welded, it is very important, and the direction of force applied. Because all this decides, these are the considerations involved in the selection of type of weld or welded joint. Type of weld or welded joint. Let's look at this design of fillet weld. Now see, sorry, transverse fillet weld. Now the geometry is very important. Just try and understand this fact. Say this is single lap or fillet joint. This is double fillet joint, double lap or fillet joint. Now we have enlarged this area for the sake of understanding. Okay. What we have considered, let small s be the size of weld, because welding is done at this point. So this is generally in the form of triangle, and it is our general habit or a practice. Let us say it is general habit that when we join two elements through welding, then again we doesn't get satisfaction whether the joint is made strong or not. Again we go for chipping hammer, remove the slag, and again we'll have a second hand over that particular second weld deposit on the joint or at that joint, known as reinforcement, and it gives us additional strength to the joint. Yes, it gives us additional strength to the joint. And how much reinforcement is generally acceptable? Otherwise it would be a wastage of material. So 10 to 15% of reinforcement is admissible in all the cases. Admissible. So now just look at this triangle, wherein triangle ABC, where we want to calculate the most critical side or length so that we can save that side and the whole system will be saved from the failure. So transverse fillet welds are designed for tensile strength. Obviously, this joint is for tensile strength. This joint is for tensile strength. So it will be pulled along and the joint will be subjected to tensile. For strength calculation, the section of the fillet is assumed to be a right angle triangle with hypotenuse making equal angles with the two sides as shown in figure. So here it is 45, again it is here 45. Drop a perpendicular from B to D at AC. Try to understand this fact. So this BD is the weakest section known as throat. This BD is known as the throat section. So of this weld. So this BD is the weakest portion in this welded joint. Hence this throat area. Hence this throat area A is equals to T into L. Let this throat length T, this T into L, here it is L, here it is the complete length. So area, throat area is T into L. Okay. And what is this? What is this S? This is side or the size of weld. How we can write this? Yes, we can very well write it. We can very well write it in terms of S, and angle and the length, entire length. So it is written as sine 45 into so S into L. Sine 45 means 0.707 into S into. So from this equation we can say that stress is equals to force upon area. But what is area? What is area? A, P into L. P into L. But what is T? Throat. Throat is been written in terms of 0.707 S this side. So it is written 0.707 S into L. L is the length. L is the length of weld, complete length of weld, and it should be less than the permissible. This is for the single single fillet weld. If it is double fillet weld, then 2 times of area, and this is the question. So I hope we have got this very basic idea, wherein what we have calculated is BD. BD we have calculated, and that is the throat length, and this throat length is converted into S into sine 45, and the equation will be okay. The next one is parallel fillet weld. That is, the length of weld will be parallel to the line of action of force. Again, the same thing, but these parallel fillet welds are designed to take shear. They are not there to take tension. Now it is for shear. So shear strength. So it is tau, load per unit area. So for this double parallel, it is 2 times of A. For single parallel, it would be P by A. Based on same throat area, we'll calculate this. The next one, combination of transverse and parallel fillet weld. So my dear friend, we have to add it. Say single transverse double parallel, single transverse double parallel, single transverse double parallel. We'll have to add it. Okay. Sometimes it is single double transverse double parallel, then 1.414 S into L, subjected to, because this transverse weld, this vertical will be subjected to tension, and these two horizontal will be subjected to shear. Henceforth, we can say that it would be subjected to both tension and shear if it is of transverse and parallel side. Okay. The next one is unsymmetrical. We may encounter this type of joint in industries wherein we have unsymmetrical welded sections. Like this portion is for LA and the length of this weld is LB. Obviously, the type of load applied is axial or eccentric, doesn't matter at all. In that case, these distances would be very important. That is small a and small b, because in this case the moment would be there. Now see the moment, and the resultant moment would be this. So therefore we can say that moment about gravity axis. So if the axis on this gravity axis, the moment would be taken, then LA, say LA into F. Obviously, what is F? Resistance offered by the weld per unit length. Resistance offered by the weld per unit length, and hence we say that LA is equals to LB upon A plus B. LB is equals to L into A upon A plus B. So directly by putting these values, you can calculate the length of welds on this unsymmetrical weld section. The next one is design of welded joints, that is eccentrically loaded, subjected to torsional shear. Now, please concentrate on this diagram, wherein we can say that this eccentric load in the plane of weld will try to topple it down, will try to twist it down, will try to have torsion, and thus these fillet welds, parallel fillet welds, first will be subjected to shear, and secondary, just look at this. Please look at this. And secondary also, it will be subjected to shear. So primary shear, tau 1 is equals to P by A, and secondary shear, tau 2 is equals to moment M into R upon J, where J, polar moment of inertia of the welded section. R is the distance of the point of the weld from the center of the gravity. Because for weld section, for rivet section, we have to have center of gravity or point of gravity of the weld section. And R is calculated from the geometry. So using these two basic equations, we can calculate the eccentrically loaded welded joint subjected to torsional shear. Last but not the least, that is Mr. Design of butt joint. That is simple butt joint. Only tension is involved. Only tension is involved. So it is sigma T is equals to P by A. And what area is all about? It is throat into length. Throat into length. That is, and that's all for today's lecture. Tomorrow we'll continue on the design of gears, shafts, and clutches. Thank you. Thank you so much.